Hello again, welcome, and thanks for tuning in to our wonderful chemistry course. Today we will talk about equations of chemical reactions, part 2. We will discuss the various types of chemical reactions, specifically for our inorganic chemistry, and the types of equations we're using. And may I make a list quickly? We will talk about a combination, addition, or synthesis reaction, the reversal of that, the decomposition, elimination, then the single replacement or displacement reaction that is also always a redox reaction. So we will also talk a lot about redox. And then the double displacement reaction, which used to be called the metathesis reaction, and the driving forces for making a successful double displacement reaction to make it work. For this we need to have a gas, liquid, solid formed. Because we use the symbols now for the physical states alongside of the formula of the reactants and products. So a little subscript in parentheses with little g, l, and s mean the physical state that is produced after the double displacement reaction. If that is the case, otherwise we use that little parentheses expression with AQ, meaning aqueous or aqueous. In other words, is the substance still completely dissolved in the solvent? Then we use AQ. That means the ions are still floating around in the solution and haven't recombined to something that leaves the premises as a solid, liquid, or gas, so to speak. Then we will go a little bit more into redox reactions, and combustion is a special type of redox reaction. That is a reaction that produces heat and light, and an explosion would even add sound effects to this reaction. But we're not doing explosions. We're not allowed to do anything here. So let's start with the types of chemical equations. The first one that we mentioned was addition. And we have 3 different names. We can say combination or synthesis. It all means the same. And this is the outcome of one product from many. So out of 2 or more, you get 1. So 2 or more reactants produce 1. We can say A plus B gives C. Most of the time, there are 2 different reactants. They can be elements, they can be compounds. Sometimes 3 things react at once, but that is not very likely. So here we have magnesium plus oxygen, as we have seen earlier when we talked about the magnesium burning for the study of the empirical formula to magnesium oxide. So this is a perfect example of a synthesis, combination, or addition reaction. Now this top one happens to be also a redox reaction or oxidation reduction, and we say a redox for short, the red ox if you like. So magnesium is being oxidized and oxygen is being reduced from the oxidation state plus minus 0. We'll go more into oxidation state as we go along. Another type of addition reaction, which is not a redox, is the dissolution of carbon dioxide in water, which produces carbonic acid. So under pressure, carbon dioxide can be pumped into water and make sparkling water that if it comes back out again, but the acid is formed that way, and that's also the acid formed when we inhale CO2, which dissolves in our bloodstream, by which we can produce an artificial acidosis. So it doesn't have to be a redox reaction, as we can see here, but many are. In organic chemistry, we have an example of the saturation of double bonds with a substrate molecule, such as bromine or water or something else, and then we get the addition product. The next type of reaction is elimination or decomposition, which is practically the reverse of the addition reaction. This a little bit. There we go. So out of one, you get many. So one chemical decomposes into fragments, which are elements or other compounds, smaller compounds. For instance, if we open up a soda pop can and we see the bubbles coming out, then it's carbonic acid decomposing back into water and CO2. Also, earlier on, many elements or metals were discovered by decomposition of the ores, because many metals are not found in the free state and they are in combination of oxides or sulfides in the geological crust. So when we decompose that with heat, with extreme heat, we can break down these ores into their constituent elements and thus collect the metals by themselves. For instance, you can decompose iron oxides and produce iron and oxygen gas. Here we see the reversal of the formation of the carbonic acid. By the way, carbonic acid is a very unstable acid and decomposes most readily into water and CO2 if it's not forced into solution by pressure. Here I have a little interesting story to tell you. When you take lime, quicklime, which is calcium oxide, and you transport it, people had to be sure that they didn't get into any rain, because the rain would convert this into calcium hydroxide, which is an exothermic reaction and starts burning all of a sudden. So this is a very interesting paradox. So rain starts the fire of this particular chemical. So here it would be a combination reaction, but in reverse we would call that a decomposition reaction. This quicklime is formed out of limestone under heat, which also produces carbon dioxide. Slaked lime is the wet quicklime, so to speak, and that is a very important chemical for making mortar and binder and plasters. The next reaction that we want to discuss is the single replacement or displacement reaction. And these are always a redox reaction, because there's always something being oxidized or reduced. For instance, if we put a zinc plate into a solution of copper sulfate, an aqueous solution, which makes the solution a beautiful royal blue, and we wait for a while, then the color of the blue solution will disappear eventually, and we will see a lot of sort of ruddy deposits on the zinc, and that is a sign that something happened. Some place has been exchanged. That means zinc went into solution. From zinc atoms, we have zinc ions formed, and copper ions became elementary copper atoms that are not crystalline yet in the metal lattice. They haven't made a metal lattice as of yet. That's why we do not see that metallic sheen as we are used to when we look at metals. So you see we have sort of a galvanic element here. Electrons are changed. Copper picks up electrons from the zinc, and zinc donates the electrons. So this is also what we call a redox reaction. So you see, this is what we call a cation displacement, because the cations of the salts or the ionic compounds here have been replaced or exchanged. Notice that we use the terminology AQ for aqueous or aqueous. That means the compound is dissolved in water, meaning it is dissociated into ions. These ions are hydrated with solvent molecules. And solid means that we have the solid form of the element of that particular chemical in our setup. Let's look at anion displacement, which is also possible. And we see here that the more active halogen will displace the less active halogen in its particular chemical combination. So chlorine, having the oxidation number plus minus 0, all elements are always 0, will substitute for bromine and kick bromine out of its combination. So it will just take its place and make a compound. So this is the anionic displacement. And there's a nice way how to test this reaction. If we take non-miscible liquids like water and hexane, then the bromine that has been produced during this reaction will prefer to be dissolved in the organic phase, the organic solvent, which happens to be in our case the top layer, because hexane is less dense than water, and it colors the solution in a nice amber color. So that is a good test for a positive reaction. If we do the same thing with iodine, and bromine is going to be the more reactive halogen or element than iodine. So you see there's a sequence. Chlorine is more reactive than bromine. Bromine is more active than iodine. So bromine can kick out iodine out of its compound and take its place, and then elementary iodine is formed. And if we do the same extraction type of test, then we will see the top layer of hexane turn into a wonderful purple color or magenta. So this is ionic displacement. So generally speaking, AB plus C gives AC plus B if it's the anion, or AB plus C gives CB plus A if we do a cation displacement. So that's the general pattern of this reaction. Now you might ask yourself, why can one element displace the other? Or what designates a more active element? The activity series, as we have shown here, lists all the elements according to their decreasing activity in this lineup, so that anything on the left can displace anything that is to its right. That means these elements prefer to be in an ionic state rather than the neutral state. There's more to learn about this, but this would go beyond the concept of our chemical course, chemistry course. But if you're more interested, you can just go to a higher level chemistry course and learn more about this phenomenon, which is extremely interesting. Now we see here a lot of metals, and the middle, or we see here hydrogen, is sort of a borderline between the more active metals and the noble metals or extremely less or lesser active metals. So you see copper is easily displaced by anything to its left, including of course zinc that we have just seen. And the most noble metal that you cannot, that has no activity whatsoever, and that's good, is gold. And before that comes platinum, then silver, mercury, copper, antimony. Palladium is also here, but it's not listed in our sequence. Now look here, we also have an activity series for the halogens, and we have already learned that iodine is less active than bromine, and chlorine is more active, bromine is more active than iodine, chlorine more than bromine and iodine, and fluorine would be the most reactive halogen. These are listed according to the so-called redox potentials that can be measured and then lined up in a table. The next, fourth and final type of reaction is double displacement. And here we see that the general idea of this reaction is AB plus CD, or cation anion 1, cation anion 2 will displace each other doubly so that the outers will combine and the inners will combine to AD and CB. This is sort of similar like the math concept of FOIL. So this is the same way you can figure out what kind of products we get. So we get we use two reactants that are usually salts, but they can be also acids and bases. And then we get two products, which can be different things, usually a salt and another salt, which might be insoluble, hopefully. Or the other compound can be just plain HOH, which is water, or it can be something that produces a gas, like carbonic acid. So it's a combination of the inners and the outers. But you always have to be careful that you write the cation first. Now, in order to have a successful double displacement reaction, something on the right side, on the product side, has to sort of separate itself from the rest of the mixture. Otherwise, we just have a salad of ions, as I will show you later. So there are three driving forces, roughly, that propagate a successful double displacement reaction. Three driving forces. And that would be number one, the formation of a solid that we indicate with the parentheses and the little s, as we see here. Now, if we take silver nitrate, and that's A and B, A would be silver, B would be nitrate, and the second chemical is sodium chloride, so that C would be sodium, and D would be the chloride ion. Then we do that inner and outer combination, and then we get the new products. So you just take the ions by themselves and then make sure that you have the right formulas. Here it's very easy because they're all plus or minus 1 charged. So silver chloride, if we look it up in the solubility table, then we will realize that silver chloride is an insoluble substance in water, relatively insoluble. Nothing is completely insoluble. So that it makes a precipitate. That means we see the solution get cloudy or opaque or milky. But silver chloride makes sort of a cheesy-like white precipitate that looks like cottage cheese pretty quickly on the bottom of our container. Sodium nitrate, however, is a soluble substance, so it will be separated into ions, and they're still floating around in the so-called supernatant. That means a solution above the precipitate. Because the solution sort of gave birth to the precipitate, that's why we call the above located solution the super above natant. And we see here, this is a positive reaction. Why? Because we can separate the silver chloride from the rest of the solution by filtration. That means we can isolate the components. The silver nitrate, or excuse me, chloride will be in the residue, as a residue in the filter. The rest of the ions will be in the filtrate. And if I drive off the solvent of the filtrate, then I can also isolate sodium nitrate as a crystalline residue. So that would be a positive reaction. That means the driving force was precipitation, which happens to work with these chemicals that I chose. Now, the next type of driving force is formation of a liquid. And the liquid that is usually formed, of course, is HOH, which is H2O liquid. It's water, so it just adds to the rest of the solvent. That means it's not ionized and therefore is a positive driving force because you can separate the product. You can certainly drive off the water and then have sodium sulfate left over. So here we do the FOIL again. We take sulfuric acid and sodium hydroxide. So this is an acid-base reaction. And this is based on the Arrhenius definition of acid bases. That means acids are proton or hydrogen ion donors, and the bases are the hydroxide ion donors. And hydrogen ions plus OH ions give, you know this by now, H2O. Then we have sodium sulfate. As I mentioned before, you first do the FOIL, or the inners and outer combinations, and then you make sure you have the right formula, because remember, the ions are in a new kind of combination and therefore have to be balanced out differently according to the Sage neutralization. So this reaction, this particular type of double displacement, we would call neutralization. And you can tell there's nothing interesting to see here, but you can tell that a neutralization reaction occurred by heat evolution, because if you do that in a test tube, the test tube will get warm, so you can feel the heat given off. So that's definitely a good sign that something has occurred. And you can separate, as I already mentioned, the sodium sulfate by driving off the solvent in an evaporating dish, as we have done before, and then you get crystals in the residue that is nothing else but sodium sulfate. The third driving force is the formation of a gas, which we indicate by little g. So the gas, and you know the gas is always trying to move out of things and go into the wild yonder, into the universe, into the atmosphere, so it will always seek the escape route. So we see here that this reaction, sodium carbonate or soda plus HCl, which is hydrochloric acid, the aqueous form, because HCl is normally a gas, but if it's infused into water, we get hydrochloric acid, or another term would be muriatic acid in the technical sense. So when we do the FOIL thing, sodium gets combined with chlorine, chloride, and H with carbonate, and we balance the new formulas, then we get these two products. However, carbonic acid at first is still dissolved, so it's AQ. But, as I mentioned before, it's an unstable compound which decomposes very readily into water and carbon dioxide. And if there's nothing to hold it back in the water, it will just seek out the outside world and bubble out of the solution. We also have, on the other hand, water as a remainder, which just adds to the solvent. So this is also a positive way of separating the two components. The carbon dioxide we don't want to collect, but we have then in the end our sodium chloride in the remaining solution. And when we evaporate the solvent in an evaporating dish over a water bath, then, or steam bath, then we get sodium chloride crystals that are very pure and we can use for our cooking. Now, one thing is interesting. What if we have no reaction? What happens? Let's say we take two chemicals and let them react with one another and nothing happens, and we drive off the solvent. How many salts should we have in the end? So what if no reaction occurs? Now, if the aqueous does not change in any one of these physical states, then we have a problem. That means there's no problem. There's no purpose of doing this experiment at all, or this reaction, because nothing happens. It just makes it even more complex. which we don't want in chemistry. We always want to isolate chemicals. So we have here potassium chloride, sodium nitrate, both aqueous, meaning both dissolved, and after the foil experiment, inners and outers combination of double displacement, then we get potassium nitrate and sodium chloride. And if we look that up in the solubility chart, and I know that these are soluble, but some people don't, so you have to look it up, and both are still soluble in water, have good solubility in water, so therefore nothing happens. The reaction practically is not successful, because if we look here at the flask, and we have all these solvated, hydrated ions floating around in the solution, which I would call a soup of ions, or salad if you prefer, free-floating ions, and we would drive off the water, then you have 4 different possibilities, because it depends on how the ions combine and crystallize into a lattice. So potassium chloride could be found in the mix, sodium nitrate, potassium nitrate, and sodium chloride. So the answer is 4 different salts will be found. Now I want to talk, before we finish this off today, we want to talk about redox reactions. Redox means that electrons are exchanged. So we can either have oxidation, meaning electron donation, meaning rise in oxidation number, or we can have reduction or acceptance of electrons, meaning going down in oxidation number. So real electrons can be given off, or electron density can be shifted within the molecule. And this both means oxidation reduction, and we use numbers to indicate these changes. Whole numbers for real electron exchanges, but also when we have a shift, we also use numbers. Thank you very much, and goodbye.